The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. On behalf of Web Solutions, I would like to welcome you to today's webinar. Before we begin, can I see by a show of hands if you can see my slides and you can hear me? Just raise a hand, click on that. Anup, thank you. Looks like Roger, thank you. Looks like we are all to go. Thank you, guys. My name is Mikhail. I will be doing the presentation of this webinar. We've got about 45 minutes or so allocated for this class. More people is joining, I can see. So it's a big topic, really very exciting. I've been working with R for a number of years, probably 3 or so. I started just out of curiosity, and it just developed into something that I feel is worthwhile sharing. Many people are looking at R as a very good tool for doing data science projects. It's not kind of a homegrown projects where you can do it on your laptops, but rather a really sophisticated system that would allow you to facilitate acquiring knowledge, uncovering trends. I have no assumptions as to whether you know R or not, and I will do a quick intro what R is. I will just highlight certain points. Definitely we have no way to cover that in any depth, but at least my task is to just get you interested and see how it compares with existing systems like Excel, maybe Python, scikit-learn, machine learning tool. So that's kind of the major idea. So very short overview of the talk, R concepts and how R fits. So that would be one example of applying KNN algorithm, just to give you a flavor of what is involved really to get things off the ground and kind of keep going. So R is it's programming language. It's scriptable, interpreted language, which is distributed under the GNU public licensing, meaning that you cannot really develop anything and hiding it. That license prevents its kind of contiguous license. So be aware of that. GNU, whenever it touches anything, should be disclosed under the same license. It's supported currently by a very active user community. What's interesting is that that community has very strong background in statistics, analytics, and generally data science. So people get confused what we're talking about, data analytics, data science. So generally we're talking about data science, which includes statistics, which includes machine learning. It's kind of an all-embracive kind of a term, kind of umbrella term for all those activities that essentially you are most likely be falling under. So it's pretty old system which has matured over a period of time. R, even though it's an interpreted language, essentially it executes commands one line by line. It can also be extended by using native C and Fortran routines. So depending on the machines that you're using, like on Windows, you can have a DLL, which essentially will give you that bridge into native code where things would run dramatically faster. R, in addition to the command line interface, also supports a number of GUI environments. We're going to talk about this shortly, and it also has built-in graphics, because one of the kind of big pillar or tenet of data science is data visualization. So we're talking about exploratory data analysis, where you need to have some good understanding what you're dealing with, so that before you start doing the wrong thing. You need to understand what you're doing. By the way, Python is picking up momentum with lots of developers. And in order to match those data science capabilities of R, Python cannot really offer anything out of the box, so it kind of borrows from SciPy, which is built on NumPy, native kind of a code for supporting arrays. Pandas, data frames, and machine learning packages like scikit-learn that I mentioned, right? All those things in one form or another are already part of R, because R was created from ground up as the language which would support all those things, particularly data frame. It's a very popular data structure which has a major influence on pandas, for example. NumPy also borrows from that native interface bridge that R has with C code. So a big picture which kind of tries to balance off R with all those things on the left. It's a little bit dated slide, but it captures kind of nicely things like scikit-learn is not showing here. It's something that is just growing exponentially. Lots of people are turning their kind of a focus on that language. But R is really something that can be viewed as a super glue. So it's a language which was created by statisticians for statisticians. And by the way, I didn't mention this. If you have any questions, don't hesitate to fire off. I'll be handling the questions panel myself. I'll keep my eye on it. There should be a questions pane. Just detach, put in a question in there, okay, and I'll do my best to answer it. If not, at least I'll give you some pointers. So on the left-hand side, as you see, we've got Excel, we've got SAS, SPSS, and a number of other things. Out of those listed here, I would recommend RStudio. RStudio, a nice GUI which just emulates the built-in R GUI, which comes with its own graphical user interface, and it has some additional kind of artifacts which would make your experience as a developer, as a business analyst, as a data scientist more enjoyable, right? RStudio also gives you a choice of having an enterprise edition where you would have a server acting as a repository of your code, where you can connect from multiple consoles using your browser. A good I guess, development model for offshore companies if you want to share it across multiple time zones. So RStudio probably is the first for you to take a look at how you can start. RStudio depends on R. RStudio in itself is just a shell, kind of like a GUI shell on top of R. But binaries are distributed separately. By the way, there is lots of criticism, particularly from the part of Python, so saying that there are lots of kind of shortcomings that R kind of has inherently in its design. One of the things is that it doesn't support multi-threading, and in order to start processing a large data set, it needs to load that data set in memory. So it doesn't have the notion of memory mapped files where you can kind of process files larger than the available memory. R supports 64-bit architectures, so the heap might be pretty big. Garbage collection is present, not as efficient as is in .NET or Java, but good enough. Microsoft early in the game realized that R is going to be big. So they purchased Revolution Analytics, which were making major inroads into enterprise, where they supported multi-core CPU architectures, where that efficient dataset processing, that massive data sets was made possible. So essentially, they got the know-how a couple of years ago, and now Microsoft is playing very nice. They have an enterprise edition for large, kind of big companies, corporate clients, but they also offer you R Open, which pretty much are same interface, same packages. They take the snapshot of the comprehensive R archive, which contains about 10,000 packages. They find kind of a baseline. It's not the latest, but it's kind of a more stable baseline, and they implement it on OpenR. So R, if you need performance, if you need all kind of those shortcomings addressed, multi-threading, multi-core support, and large data set processing at one go, just take a look at Microsoft R Open. I'm in any way associated with any of those companies. R is just, that's the topic, right? But Microsoft is something that you can start looking at. Okay, so Microsoft is there. Again, our features. Just take a look at a number of coding idioms that might kind of shed light on how things are done. So let me just highlight a couple of things. I don't expect you to be familiar with R, and particularly with R syntax, but I will give you a very kind of quick, high-octane kind of a walkthrough. So that's the way to build a vector. So there is no arrays. Everything is a vector, list, or we're going to talk about data structure. C is the way to build the vector. This function is called so because it's derives from the combine world. It's combine, you're combining those elements, right? We've got a line. What's interesting, you can apply arithmetic operations like multiplication, rising to a power, division across all elements by just specifying the reference to the vector. You can combine vectors, as you see. We can do print. We can do sum. So sum is similar to what you would expect, like in other scripting languages, like Python, for example. But mind you that we are working on vectors, right? And essentially just follow the logic what we are trying to achieve here. I guess there are some comments. I'm not going to spend much time on it. But the point is, developing in R, it's a pleasure. Really, I've been like working with a variety of languages, Java, C, and R is just kind of gives you a lot of flexibility. It's not very all-embracing kind of a thing. It does lots of things, but it does those things which are specific for your data science tasks at hand very nicely. Partitioning your dropping columns, adding columns, providing some plugs for holes in your data sets is extremely nicely done. Okay, there are some caveats to be aware. For example, if you trying to do certain things on vectors, just doing additions of vectors, then certain things might kind of creep in. For example, if you've got vectors of different lengths, then vectors would start recycling some slack to match the length of the longer vector. So be aware of those things. I'm just telling you up front that it's not all that kind of nice and fluffy. It sometimes can be pretty kind of scary. R is a fully functional programming language. In addition to supporting the traditional procedural language, like imperative programming paradigm, functional programming elements can be found, like reduce, map, filter. So that's what you would expect in languages of that caliber, of that category. So interestingly, that reduce takes the normal kind of a syntax as you would expect, but it also has this kind of a notational syntax. Map, filter works as well. So you pass on, those are high order functions. You pass in on functions which are lambdas, which perform a specific operation. A very appealing consideration for those who are just looking for a tool for their data science projects is data structures. R, in addition to primitives like strings and numbers, it supports very useful structures. You would expect an array, right, a list. So there are two types of flavors of that list. There are vectors and lists. Vectors essentially are lists which have elements of the same type. For example, numeric or a string, right? And it's the most popular. Lots of things kind of built around vectors. Lots of algorithms for machine learning for data science are built on vectors. Lists are vectors, but they can contain elements of different types. They can contain vectors as a lists. It's more versatile and not so often used, but lists are there. Matrices are multidimensional forms of vectors, two-dimensional, more precise. Essentially, matrices have also elements which are of the same type. There would be a slide which would describe how easy it is, just to show, kind of illustrate, showcase how easy it is to do linear algebra with R, because it has matrices built in. And data frame, that's kind of the Cadillac of all structures. It's matrix-like, but it's more of a table in relational databases, because it has columns of different types, and as data scientists refer to those columns of properties, those are features or variables, right? And you've got rows, observations. You can have multiple types, so that's what differs data frame from a matrix. It's kind of looks like a matrix, but columns can have different types. It's kind of a composition of vectors of different mode, of different type. Data frames, very similar to what you would find in other systems like SAS, SPSS, and Pandas borrowed that very productive idea from R. So matrix algebra. So as I said, matrices are built in. It's very easy to create matrices from vectors. You just create a shape. Shape is a number of rows and columns. I'm not showing that kind of that constructor function. Essentially, it's a matrix, as you would expect. You pass in on a vector, which might contain like several millions of records, and you specify how many columns or rows you would like to have. And the system would just apply those indexing in a way that it would very quickly transform that vector into a matrix. And then you can apply all those operations that you see here. By the way, those things are built in the language. It's not, some of those might come from some packages, but those packages essentially have been created to be part and parcel of the language. For example, transposing the matrix, multiplication, doing the inversion. So that's something that I guess you can do by hand using Java, but you will have to implement it or use a specialized library like a jar file. You can create quickly kind of a knock-up matrices from vectors, column-wise or row-wise. This is very productive when you start doing that data munging, where you do certain things that kind of follows your data logistics type of pipeline. You need to process data. You need to bring the data to the form where you can start your data science projects. So data science is not about, for the most part, applying models like support vector machines, maybe random forest or whatever, as the bulk of effort is spent on pre-processing data. So if you look at that kind of a pipeline of the workflow of your data science projects, you start with data ingestion and you elaborate on that, you enhance data, you drop outliers, you remove certain kind of things that you don't trust. Lots of things might happen before you really have data primed properly, prepared for being fed into your kind of a clean room, your kind of a data science lab environment. So all those things, they just happen magically. In case of Python, you would need pandas, you would need NumPy, which sometimes kind of get in the way. So if you're new to those things, you can get stuck. Documentation can help, but certain things would require you to like figure out. And all that effort has already been spent by our developers who have all those things, right? You can have lots of, I guess, mileage out of that engine. So R is not done in isolation. It's not an island which kind of just resides somewhere in that ivory tower of data scientists and statisticians world. It's essentially a very I would say embracing language. You can import and export data in a variety of formats. You can connect to a relational database. You can read, for example, Excel spreadsheets. It would, under the hood, it would instantiate on Windows the Excel ActiveX. It will do that kind of out-of-process communication, and it pull out the data. Excel, while it's extremely powerful and widespread tool, has some deficiencies until version 2007, which has happened, I don't know, like 11 years ago. There was a hard limit as to the number of rows that it supported. It was 64,000. Now they support around 1 million. Beyond that, I believe you cannot really do efficiently unless you apply certain kind of proprietary extensions. There is no such limit on in R, meaning that you can take multiple Excel spreadsheets and you can use something like R-bind operation to get all those things and bind them together so that you've got a multi-million kind of a row, as long as you can get it into the memory. Because one of the pain points of R is that it needs to read the whole structure into memory. So for that, you need a 64-bit R support 64-bit architecture, so you can heaps beyond, I don't know, like 4 gigabyte constraint. Okay, data format, which is a very good kind of property of big data, not so much size, but as its variety, like CSV, JSON, ASCII, XML, all those things are supported. And your data might come just in text, comma separated value, or character separated value, but you can also have feeds like RESTful services, JSON feeds. It also understands a variety of statistical platforms, formats used like Stata, SPSS, which is a fantastic thing, meaning that you have yourself a tool which costs you nothing, as long as you don't use like RStudio Enterprise or Revolution's Analytics Enterprise Server, you're good to go. And your laptop is essentially that the actual platforms that you will be using. No kind of investment on your part. The reverse operation is also supported. You can get your objects, whatever you have processed in R, and you can export them. It can be Excel spreadsheet and specially crafted artifacts to be consumed by other platforms. Interestingly, when you work on a session data science project, everything is stored on a heap and you can serialize it. In case of Python, you would need pickle or something like this to serialize it. In this case, it's just, again, part of the language. Of course, if you've got large data sets, you are better off maybe to delete those objects before you serialize and read those objects when you need at runtime rather than serializing them, because otherwise you would be kind of trashing your persistence. Data visualization is part and parcel. It's just embedded in R, but it's not the whole truth. Only graphics package is embedded, which does you lots of things for free. You can build plots, histograms, pie charts, scatter plots, whatever. Your imagination is the limit. But some people tend to use some additional external packages like Lattice and ggplot2, which kind of give you a little bit more on top of what graphics gives you. And it's kind of more elegant. Certain things have nice kind of a grayish background where you would expect it to be like white. It's kind of has a more artistic bent, gives that kind of a feel that it's more kind of a sophisticated graphics, but in most cases it's just maybe an overkill. But again, you have an option. You are not constrained in any way or form by just having something. Again, those things downloadable, installable with no strings attached. In many cases, you can get by just doing that descriptive statistics, just getting a sense of what your data is, like standard deviation, variance, mean, what's not. Those functions are part of the language. Again, the language was built by statisticians, and you can get those things like mean, standard deviation across a vector, across a matrix. It's kind of aggregate values. Summary functions. So whenever you start working, in many cases, summary would be your way to get a very kind of a deep insight into what's happening. For example, if you've got a vector, you can pass to the summary function. It will do kind of a introspection of all the elements of the array. It will find the minimum, maximum range, and quartiles. It will do the same thing on a matrix. And essentially, you have a very good idea as to what that vector is with minimum effort on your part. Again, very high octane, very powerful function. For example, if you've got a vector like this, where it's just, I guess, a sequential powers of 2, you can apply a predicate. You've got that vector, right? It's a vector, it's not a variable, right? And you have this predicate which you're passing on to summary. It would identify this kind of a function as a logical, that's mode is a type, and it would perform a very nice I would call it executive summary, if you will. It will give you a number of elements which satisfy this predicate and which don't. Like in our case, it would be 6 elements greater than 5, and only 2 satisfy. Not available, meaning that which missing data or not convertible or something, not satisfying this predicate are 0. It's a very good way to create heat maps, like in Excel, like in modern Excel. You can have this blue, gray, green type of scenarios. Very nice, because in certain cases, that's exactly what you need. You've got a data feed, like for example, from a sensor, like the Internet of Things. You've got this continuous like flow of data, and you just apply kind of that valve, that kind of a gateway, checking if it's what's happening. Are we above or below? Essentially, you can use R in that scenario. For data science, really, we are kind of approaching what we are supposed to be talking about. R implements a great variety of algorithms, whether it's supervised learning or unsupervised learning. It doesn't do kind of a very extensive things like TensorFlow or kind of a more advanced things that would require probably using GPUs, graphical processing units. But all the traditional data science algorithms for classification, clusterization, regression are supported, right? And what's interesting, lots of those packages have a variety of implementations, meaning that you have always that task to find a good balance between accuracy, speed, and handling certain kind of situations like cutting on, overfitting, kind of boosting your performance, and you will be able to find the algorithm which matches your use case. In case of other systems like Python, for example, scikit-learn, you can do this customization in the actual class or function that is provided in a particular module. But in R, you can do the same thing, and on top of that, you have a possibility to have another implementation of the same thing, which would probably just give you certain things, certain properties of the execution runtime, which would satisfy your needs. Okay, so what we have here, just very quick overview of supervised versus unsupervised machine learning. So supervised learning, you've got a target variable. Usually it's something that you want to predict or estimate. Like for example, speed, you perform a task of calculating the braking distance for a speed of a car, and the make of a car and the road conditions. So that regression would help you. Classification would help you to have certain models to operate on labeled data, where you have human involvement deciding on what class or label can be assigned to a particular observation. And then the system would learn, it would be trained on based on that observations, and then it would perform classification, right? In most cases, it would be a mathematical formula of some sort. Unsupervised learning is what machine learning is all about, pretty much. It's opposite of supervised learning. Your involvement as a data scientist is minimal. You just need to say just a couple of things. Like in case of k-means, it would be number of clusters that you would expect. And you can do lots of things with that. R supports those. And again, you have a number of implementations. Sometimes what you can find kind of a bit of a kind of a grievance is that certain algorithms that not fully kind of help pages are good, but those are written by statisticians for statisticians, and certain things that they're alluding to, that are referring to, might not be clear. So if you're new to data science, many algorithms, they kind of stand in the way. They don't really show the whole thing. Like for example, you've got KNN, and okay, you can kind of train it, but what else? What's next? The next step would be do prediction. So, but it's kind of maybe missing in that kind of documentation, because people would expect that you would be able to kind of do, in this case, scikit-learn probably a more transparent system. You would be able to see how things kind of are put together. And you would see a more complete kind of a flow, like you would do that kind of data partitioning. You would apply training cycle. You will do prediction, not just one vector, but you would do prediction across the whole bunch of records, and those labels that would be produced, those classification labels, you can tie them together and build confusion matrix just quite straightforwardly. Right, in R, it's kind of lots of assumptions are made, and if you're new, you would be kind of at sea, I would say, not very comfortable. But with time, you can become quite productive. So supervised learning, that most popular one come to mind: decision trees, random forest, naive Bayes, KNN, regression, multiple locally weighted. All those things are possible quite easily. Unsupervised learning, very popular, k-means, other algorithms are supported. Lots of efficiencies, special implementations, dealing with certain situations, with outliers, with kind of overfitting. Just to give you a flavor, as that's what I kind of promise you, you have a situation where you need to do kind of a basic regression to build a straight line, like a linear regression, to fit that line so that it would describe some trend. It may be sales trend, it might be whatever the case might be, growing and kind of decreasing fat, kind of building up your muscles. And believe it or not, that's a function that actually ties together. That's LM, it's kind of a linear model, and that's the fitting. That's essentially the training. You've got X, which is a vector of observations. It's an explanatory or independent variable. It's a vector. And we've got a tilde operation, which actually has denotes that we've got a relationship between that Y, which we would like to predict. This is a regression model that we are building. Essentially, we are calculating that MB or A0, A1, whatever kind of your background in statistics 101 is. And it will give you, if you do it inside of a summary, if you do summary and you pass on that LM as a function, so summary is kind of a high order function, and it polymorphically act on that LM, it will invoke it, it will do lots of introspections, and you will have a very nice report stating confidence interval and lots of things for every parameter. And by extension, that kind of a single variable regression can be extended to that multivariate regression form. Again, we've got that dependent variable, which we're predicting, and we've got those predictor vectors. Again, those things are just extremely, it's clear to understand what we're doing here. We essentially say it's just notation. I would say it's a domain-specific language of sorts, which tells you, it's kind of SQL. Guys, that's what you need to do in order to obtain the results. Those things can be columns from a data frame. They might come from kind of different vectors. So those things essentially are reusing the variable. If you have seen what's called trend function in Excel, it's just non-comparable things. Very compact in R, very verbose in Excel. It's kind of a macro, if you will. And a very good compact example of what an algorithm can give you. Like, we want to do KNN, which is a classification algorithm used extensively in kind of identifying if an email is spam or not spam. It can be essentially it's a classification algorithm. I'm not going to give you lots of kind of a background information of this, but the point is, this is just one-liner. That's what you need to do. Several things are happening. Again, for the sake of the full disclosure, you need to load that classification library. That's the way how you do it. And then that CL is kind of one of those things that you would expect to see in any. You can do it. You will have to do it also in Python. Essentially, you just need to create. When you do training, you need to have those labels arranged in a way which would facilitate that learning, that training experience. So essentially, we replicate S so many times and N so many times. So essentially, the system, when we perform kind of there's a source, this is a test data set that we want to compare, the system would produce something like this. It's a very generic one, and you'll have to do certain things beyond that. But the point is that the whole thing is just one-liner. I would say two-liners, probably. Okay, so our offerings, we have a number of classes in the data science field, but we also feel that R programming from the ground up, which is a 2-day class, is absolutely indispensable for those people who want to maybe switch if you have some kind of pet peeves or grievances with Excel, licensing, otherwise, or you would like to have a tool where you would be able to kind of move towards the data science more aggressively. So that's the class for you. It's pretty much ready. It's just the build time to build that stuff. Okay, so any questions? We've come out with lots of ground. I understand it was a little bit, I would say, very sketchy, but anything that you would like to hear me before we close the session? Yeah, for the most part, you will be working on kind of a standalone on your desktop computer, laptop. R is supported by, for example, Apache Spark, in addition to Java, Scala, and Python. R is also used on Hadoop. Apache Mikhail is doing some interesting work in this field, meaning that you are not limited to your kind of a desktop environment. You can efficiently run R on a cluster of machines. So there are ways to do that. R on Hadoop, and particularly that Microsoft Open, R Open, is a good 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 way to start. So the question is, I'm new to data science. There would be several like me. Okay. Can you please suggest the ways to learn and implement them? If you want to embark on that path, data science, definitely you would need to have some background in statistics, very basic ones like what mean is, what standard deviation is, correlation, and then moving towards data science is not about a particular language. Like I know R or I know Python. That's it. You would probably be better off if you can combine R and Python. But I would start with R because it gives you a very quick kind of a start, a very big kind of a kickstart to get. Lots of material available. By the way, I cannot really recommend any because with every coming month there is another kind of interesting tutorial coming up. Because it observes exponential growth. You've got very good YouTube presentations, lots of in public domain. Just start slowly and don't get frustrated. Probably it's not kind of picking up a language. Syntax you'll pick up probably in a week or maybe in a couple of days, depending on your background. But really mastering all those things, it would probably take you, I don't know, maybe 12 months, maybe a year and a half, 18 months. So be kind of a slowly adopt that kind of a philosophy. The philosophy should be that data science is about having that a little bit of being a little bit of a mad scientist, where you would have things that you'd be a hacker, hacking up algorithms, setting up, tearing down. It's kind of a big big journey, I would say, and it will never stop. But you can start at least with learning R. R will kind of force you to adopt those things gradually. Another question, can you please compare with some other frameworks out there like TensorFlow, CNTK, Caffe? Well, TensorFlow, it's definitely whatever Google is offering. They expose the API through Python. That's really machine learning. You've got pretty much those neural network. It's machine learning in its purest form. R, it's not in that area at all. It doesn't require accelerations. I'm not familiar with CNTK or Caffe to the level where I can kind of intelligently talk, but most of those systems, they require some sort of acceleration. And it's a brute force for the most part. Essentially, you feed that kind of a continuous training material, images, or I don't know, voice samples, and what's not. And then the system would gradually develop kind of expertise in how to discern, how to understand what's coming in. Is it a visual? Is it voice-based? And in most cases, they require some acceleration, like GPUs, right? It would be an array of GPUs which would be doing that stuff. It's a brute force. In many cases, it can be avoided by just applying it more intelligently. But I guess we've got that power now, and people don't really care. If you don't have it at home, in your basement or in your attic, then you can borrow it from Google. They would be happy to provide you with the environment where you can set up interface with like their TensorFlow or other systems. Okay, so I would compare probably R with maybe Apache Spark. I would compare R with maybe Python, scikit-learn, or SciPy. So those would be comparable things. Okay, any more questions? Okay, guys, thank you very much for attending. I wish you every success in your future endeavors. All the best. Bye-bye.